Hello interwebs, welcome to Let's Fix Computers. This video is going to be the start of a new series talking about BIOS, what it is, what it does, and what stuff we can do with it when repairing computers. Now, I'm not entirely sure what the full scope of this series is going to be yet, but I know there's a few areas that I do want to talk about, so we're going to cover those and see where this goes. So for this first video, I want to show, or rather at least recap, stuff that you've seen me doing before. So how we do BIOS updates on a computer that is either booting or not booting. And this might be for security updates, or it might be for feature or hardware support updates, or it might just be because the existing BIOS is broken and needs to be reflashed to get the computer to start again. So in future videos, we're going to talk a bit more about the BIOS startup sequence, its reset sequence, and subregions within the BIOS that are of interest to us as repair technicians. I'd like to dig a little bit deeper than my current knowledge as well and talk about BIOS hacking for custom settings or the ME region and other things like that, but we'll cross that bridge if we get that far. For now, let's run the intro and talk about hardware. Okay, so first things first, are we calling it BIOS, UEFI, or firmware? Well, it's kinda all of those things. In the strictest sense, Universal Extensible Firmware Interface, or UEFI, is the correct term here. UEFI has been a thing that your motherboard runs on PowerUp since the mid-noughties, and BIOS is an antiquated term. However, BIOS can also just be a catch-all term here, and so can firmware. So I'm just going to use these three words interchangeably. So unless I say otherwise, it doesn't really matter, because in the scope of this series, they're functionally the same thing. Unless you're working on vintage hardware or something like that, it really doesn't matter. So firstly, what is BIOS? At the most basic level, it is code that is saved on the motherboard that tells the computer what hardware it has, what's connected to it, and how that stuff is configured. Modern UEFI is actually a tiny operating system that gets loaded on startup, and this is one of the reasons why updates are so much more important and prevalent than they used to be. 10 or 15 years ago, you'd never even bother doing a BIOS update unless there was some kind of fault. And there might not even be any updates available unless there was some major issue that had to be fixed on that particular board. But today, though, a mainstream motherboard might get 2 or 3 BIOS updates a year. And the underlying code for those updates that gets written by Intel and AMD, those get even more updates than that. For this video, I'm going to demonstrate this A620 desktop motherboard. It's a low-end AM5 system, so it's modern, but it doesn't have any fancy features on it, so it's a good real-life case scenario here. Laptops are not worlds apart from desktops for BIOS, but they do have a bit more variation to how their BIOSes are set up, and the older ones can have some wacky configurations on them. So we'll look at those on a case-by-case basis. For the time being, a desktop motherboard like this works as a good baseline for a "this is the norm" case study. So the two normal update methods that you're probably already familiar with are either the internal update utility that you'll find in the BIOS called mFlash, qFlash, EasyFlash, whatever the brand has specified it as, or BIOS flashback. The internal update is the easiest and most direct method, and that's what most people are going to be familiar with, and that is the most recommended way of updating a BIOS. BIOS flashback needs to be supported by the motherboard, and the usual signs that a board actually has it will be that there'll be a specifically marked USB port on the back, and also a button nearby somewhere saying qFlash or BIOS Flash or something like that. The actual support for flashback is generally built into the PCH, and most motherboards have it, but it's up to the motherboard manufacturer to implement that hardware on a specific model of motherboard. So even though it's built into the PCH, that you still actually have to put the wires connecting that all up, which is why it's not everywhere. Any additional wiring in a board costs more money, and that's something else that you're going to spend on a upper version of the motherboard. Now, BIOS flashback's advantages is that it doesn't require a working CPU or RAM, and it can update or recover a board that is bricked or has an incompatible CPU. but the downside of it is that it's kind of finicky. The update has to be a specific file name on a drive in a specific port, and there's little to no feedback about what is actually happening when you do a BIOS flashback. There'll be an LED on the back that will flash either slowly or quickly or not at all, but it's always hard to find information on exactly what the flashing means and what stage of the flashback you're up to. Generally speaking, you would plug in the drive, push the button on the back, and just wait for 10 or 15 minutes and hope for the best. It's good in a pinch, but I prefer to see what's happening when I'm flashing the chip that tells my motherboard how to turn on, so not ideal. And in addition to that, that's still not going to help you if the board is completely scrambled or the board is dead. So flashback is helpful, but it's not a replacement for knowing how to program a BIOS chip. So what if we do if the board is dead and we can't do either a BIOS flashback or the internal update? Well, that's what we're here for, so let's actually get into the technical stuff now. The BIOS is stored on an SPI ROM chip, and this is the modern equivalent of an EEPROM. It's non-volatile flash memory. So firstly, just to clear things up, this chip does not require constant power to maintain its settings. That's not actually what the BIOS battery is for, but we'll talk a bit more about that in a future video because it's a bit more complicated than that. So anyway, modern systems use 25 series SPI ROM chips that store a BIOS image, the BIOS settings, and miscellaneous data like serial numbers and sometimes data for things like Ethernet controllers and that kind of thing. These chips are generally either SOP8 or WSON8 packages, with the latter being the more modern design. WSON8 is what we've got on this motherboard here, which I'll talk about in a moment. Both of these can look a little bit like MOSFETs at first glance, but you can usually single them out because there won't be capacitors or inductors near to them as you would normally find near to MOSFETs. There's no actual set place to put the BIOS chip on a motherboard, but there's definitely a few common placements and patterns that you can look out for. Firstly, the BIOS chip is going to be close to either the CPU or the PCH, so it's going to be somewhere in this region here, or it's going to be somewhere down in this region over here. It's often either marked by the silk screen, that's the white writing and the white lines on the motherboard, and it will be marked either explicitly as BIOS chip, or it'll have a big white box around it, highlighting it on the board. It's also worth noting that on some boards, especially on laptop motherboards, you might find that there's more than one SPI ROM chip on the board, because things like Thunderbolt ports also have firmware that will be stored on just a smaller ROM chip. So when you do suspect you found it, we do need to actually verify that that is the correct ROM chip as well. And finally, of course, there is just simply looking at the chip markings. So Wimbond, GigaDevice, and Macronix are three really common brands that specialize in these SPI ROM chips. So if you see one of those brand names and a chip number that starts with 25, then 99% that's probably the BIOS chip. So let's have a look at this one and find out what it is. So here's the chip on this motherboard. It's upside down with the current orientation, but as you can see, it's a Winbond 25Q256JWEQ. And if you're thinking the solder points on that look a little bit rough, well, this is a reshoot. I've already taken it off once. So anyway, so that's the chip we've got here. Let's look up the datasheet for this chip and find out more about it. So a quick Google search will bring up the datasheet for this that tells us a bit more about it. So it's a 1.8 volt, 256 megabit chip. So if you take 256 and divide it by 8, then you convert bits into bytes, which gives us 32 megabytes. So it stores 32 megabytes of data. So we want to program this chip, and for that we need a programmer. So I've got a couple of common examples here. So this one here is a CH341A, and this guy is extremely cheap and well supported, but the catch is that it's horrifyingly slow. On the plus side though, this is the 1.6 version, and the 1.6 and onward versions have a little built-in voltage selector switch on the side here, which is extremely useful. You need these because different chips have different voltages, hence this one was a 1.8 volt chip. There's a very common version of this on a black PCB that is even cheaper, but it doesn't have the voltage level shifter. There's also some possible issues with its pull-up voltages, but that's a big controversial topic that I'm not going to go into. But since this version exists, I think there's zero reason ever to own the black PCB version. So yeah, this guy is very reliable, well supported, but slow. There's also this new one here. This is a CH347, and these are sort of starting to become the new hotness. It's much faster, but it also doesn't have a level shifter on it. And also, because it's fairly new, support seems to be a little less mature than some of the other programmers. So I'm still testing this one out myself. I've also got an RT809F programmer here. This guy's got some neat tricks. It can talk to monitor BIOSes through either a VGA port or a HDMI port on it. And is also reasonably quick. And the software for it is also a little bit smarter with regards to how it handles certain BIOS formats. But again, it lacks a level shifter, and honestly, it's kind of too expensive for the features that it doesn't have. I actually had problems getting this to work on Windows 11 when I was preparing for this video, and honestly, I don't care enough about it to actually solve those problems. So that brings us to my main programmer, which is my current go-to. This is an XG Pro T76, and this is the latest in a line of what are considered to be the best general purpose programmers. They're fast, they have built-in automatic voltage level shifting, and as you can see, it can handle 12 and 16 pin chips as well, in case you want to play with like vintage stuff and that kind of thing. Even if you get one of the older versions of these, I would strongly recommend an XG Pro. I should have bought one of these sooner. They're worth every penny. So how are we going to get this into this? Well, there's three methods that I'm going to show you in this video. The first method is to desolder the chip from the motherboard and then put it onto one of these adapters. So here's I can solder it onto this little breakout board that converts us into these pins that will then slot into the programmer. Or I've got a little socket adapter here where this one, I can actually open this little door here and the chip will drop into there, and then that's just a press fit, so it doesn't require me to solder it to the adapter. These are great. They've really come down in price and they're now very affordable. They used to be weirdly expensive, but now they're cheap and widely available on AliExpress. And if you've got a SOP8 chip, here's a socket adapter for one of those. So this is a nifty guy as well, and again, doesn't require soldering to the adapter in order to put into the programmer. So that's less soldering work that you've got to do. So desoldering the chip and putting it directly in the programmer is my preferred method. It is extremely reliable and it takes out a lot of other unknown factors. But the downside is that you need the equipment and the skills to do it. Now, if you're a technician, then you should already have these things. If you're a shop technician, you really ought to have yourself a soldering iron and a hot air station, and you should be practicing desoldering chips from boards just for modern board repair. In my opinion, it's a necessary skill if you're trying to run a modern repair shop. However, if you're trying to DIY repair your own bricked motherboard, and you're trying to do that at home, then yeah, I can kind of see that desoldering the chip kind of blows out the scope of the repair. So in that instance, I would 100% understand if you want to find another way that doesn't involve soldering work. So the next common way is to use a clip, which is one of these guys that I'm showing a picture of on screen. I don't have one of these because I think they suck and I hate them. However, I do have this guy here, which is very similar. So firstly, a clip is designed to clamp onto the chip itself, but the issue is that it's really difficult to get a good connection to the chip this way because there's very little to actually clamp onto. And if you have a WSON 8 chip like this motherboard does, you basically cannot clip onto that. There's probably going to be some people in the comments that are like, oh, I've got this Super Wizzo clip that can do that. However, often they're kind of ludicrous. The only ones of those I've ever seen are ludicrously expensive, and no one that I take seriously uses them. So make of that what you will. So yeah, this version here, this is a slightly different thing where it's pogo pins instead. So if I hold this up, you can see we've got a little set of pins there, and when I press down on this, the pins poke through. So the idea is that you press this down on top of the chip, and the pins will poke down onto the pins of the chip. So these will work on WSON 8 chips as well as SOP 8 chips. And I've done a little bit of practicing with this, and it's okay. The problem is that you've got to hold it down against the chip while you're doing the programming. And for just a simple read, that's not too bad. But if you're actually writing to the chip, the erase, check erase, write, verify cycle takes quite a while, and it's harder than you'd imagine to hold it dead straight and still for that amount of time. But I'll show you some examples of using this in a bit later on. So it does kind of work, and certainly I think this is a viable option. It has drawbacks, but if you really don't want to desolder, it's not bad. I think these are pretty good. And then the third option is mostly desktop boards only, and that's the SPI header, which is this row of pins down here on the motherboard. This header is common on most modern motherboards, and it actually gives a direct connection to the SPI bus that the BIOS chip is on. The annoying thing is that the pinout of this header isn't standardized, so you'll almost certainly need a custom cable to use it. So I've made up a custom cable that matches this specific motherboard, but it's kind of luck of the draw whether this would work on other brands of motherboard or even other MSI motherboards from a different time period, you know. So if you want to use this method, you might need a couple of these cables, or you might need to be prepared to repin this depending on what board you're working on. However, this is a pretty reliable means because once you've got it plugged in, you can go hands-free. So in the future, I could see myself making up a couple of these for common motherboard brands. So yeah, I'll show you this one as well. So let's get started by showing you guys the de-soldering method. And because that's my recommended one, and it's the most straightforward one to demonstrate. So I'll just take this setup apart here so we've got a bit more access to the motherboard. So to desolder this chip, I'm going to use my hot air station, and I'm going to be blowing generally in this direction toward the camera to avoid these capacitors, this plastic connector, and the hold down bracket here. You can mask these off using heat resistant tape and stuff like that, but in this instance it's not tight enough that I think that's necessary. Some motherboards there's so little space to work in that you will have to do a bit of masking, but I think we'll be okay here. Oh, my tweezers aren't wide enough. There we go. Right, so spoilers, I have already taken this one off before, which means it came off really easily there because it's already got leaded solder in there. Normally they take a bit longer than that to heat through. You have got a ground pad there, which will fight you a little bit. You will need to put heat into that to get it to flow. But be patient, keep the air moving, and blow away from sensitive stuff, and you'll be fine. So now I'm going to load this guy up into my WSON 8 adapter. There we go. And because I'm using the T76 here that has automatic level shifting, I can just drop this directly into the programmer. If I were using something else that doesn't have level shifting, like say the RT809F here, then what we would need to do is put in a 1.8 volt adapter. So here's what a 1.8 volt adapter looks like. So as you can see, it's literally just a pass-through. It plugs into your chip socket and gives you another chip socket, but this one has gone through this little regulator chip here that level shifts everything down. So you would plug that in like, let's see, pin 1, so that would go in like that, and then I would plug that guy in like that. Whoops. And that would be the setup for a 1.8 volt adapter. So you can see why having a built-in level shifter is extremely handy. It's not strictly necessary, but having one sure is useful. So let's load this guy up. programmers will generally have markings on them to indicate what way around the chip goes. So my one's going to go in like that. All right, that's ready to go. Let's plug it in. So I'm going to go ahead and auto-detect the chip. So I'll click the auto button here, and it will detect the chip for me and give me a rough guess. So here's a list of guesses it's got. So we had a Wimbond 25Q256JW. So that's going to be one of these. And we had the WSON 8. There's a good chance that any one of these on the list will work because they're all extremely similar, but an exact match is always the best. So let's select that. And now I'm going to go ahead and read the chip. All right. This is a big 32 megabyte chip, but as you can see, the T76 shreds through that in no time at all. If we had a CH341A here, I would actually get up and go and make a coffee at this point. It will take that long. But yeah, T76 go burr. So it's read the chip and then it read it a second time in order to verify. So the verify means it read it a second time and got exactly the same result. So it's confident that we had a successful read. So let's go back. So now that read is done, the data's been loaded into our buffer, which is this area in the middle here. And if I scroll down a little bit, you can see we've got some data here. And this is all binary data, so most of it is not human readable, although there's sometimes random strings in there that you can get snippets and fragments out of. We'll look a bit closer at this data later on in the series, where I'll show you how you can open this in something that is a bit more accessible and start discovering information from it. But but if nothing else, the point is we can scroll down a bit here and see that we have some data. So the first thing that we want to do whenever you're doing anything involving manually reprogramming a BIOS is you want to save the dump. So this is a dump of the chip. It is a dump of the contents of the chip, and we're going to save this as a backup. So if whatever we do to this goes horribly wrong and sideways, we have a backup of how the chip was when we first looked at it. So I'll hit save. And I'm just going to save this into a working folder that I've got for this motherboard. So we've saved that. File saved. Good. So we always save the dump. Always keep a backup of the stuff, because you never know what you might need later on. So now we've done that, we want to load up the BIOS that we want to program to the chip. So the first thing you want to do is go to the support page for the board in question and download the latest BIOS. And the latest BIOS will do fine. Here's one I downloaded earlier on. Now, from the loading screen here, we can have a quick look. And as you can see, the downloaded file is 32 megabytes, 768 kilobytes. And my dump file is identical plus 1 kilobyte. Now, my dump file is slightly larger because the XG Pro software adds a little bit of metadata into the save file. However, this is functionally, for our purposes, these are the same file size. So that shows us that we've got the same amount of data there. So I'm going to open this file that I've got here. And the format is 1K5, and that doesn't mean anything. That's just version numbering that's used on BIOS files. The format is still going to be a bin file, a binary file, so you can ignore extensions. The only one that actually matters is when you have a cap file, CAP, and that means capsule file. And we'll look a little bit closer at one of those a bit later on in the series. However, they behave slightly differently, so we'll get back to that one. So let's open that. And now we've got that downloaded file loaded up into our buffer, and we're going to program it to the chip. So when programming the chip, we're typically going to go through a sequence of turn off write protect if it's enabled, erase the chip, check that the chip has been erased, program the chip, and then verify that programming was successful by reading it again and checking that you get the same thing that you programmed to it. So for the XG Pro software, these tick boxes are all down here in the corner, so I've got all of those on. And most software will have that somewhere around near the programming button as well. So I'm going to hit program, and I'm going to hit go. So erasing the chip is usually the bit that takes the longest. And this is the main reason why when you're programming a chip, you want a hands-free solution. And the problem with clips or anything that you're having to hold in place is it's hard work to hold it in place during this part, because this is the bit that you can't really make any faster. Right, programming is complete. So we're done with this. And now we're ready to pop this guy out and put it back on the motherboard. So let's do that. And the other thing I'm going to do is I'm just going to pop out the BIOS battery to do a reset as well. Should have taken this out before. Like I said earlier on, there's no power going from here to here, contrary to popular belief. So there's no damage by leaving it in. However, motherboards will often get pissy after you've messed with the BIOS and haven't reset it. So we take this out just to make sure it actually gets a BIOS reset. And this thing should be ready to go now. So let me just plug this all back in and turn it on. And as with any BIOS update, it's not unusual for the board to take a longer time than usual to post after this, because it'll probably want to RAM train, and because of the BIOS reset, it might do a couple of false starts or 1 or 2 power cycles and things like that. So don't panic if it doesn't immediately spit out a picture. Just be patient and give it a minute or so. And there we go, that's our update done. So as you can see from the BIOS build date, that's now 27th of October 2025. So you can see that is updated from the 2024 BIOS that was initially on it. So that's how we know that the BIOS update was successful. So that's a successful flash. So now for the next bit, I'm going to show you how to do the in-circuit flashing. And we're going to start out by using the Pogo pin adapter. So for the Pogo pin adapter, I'm going to use my XG Pro programmer again. And this time we're going to plug in this affair. So I've got to find pin 1 and plug that guy in like that. And turn you on. So the way that we're going to hold this thing is I'm going to align the pin 1 stripe here with the pin 1 dot on the chip that is in the lower right from my orientation. So we'd have to hold it like so. So I'll just position that just so the plastic bit is on top of the chip. And then I just press down on the pins like that. And now I know in advance that the pin detection is going to be really sketchy on this. So I'm going to switch off pin detection and just go for a basic read here. And here we go. Reading flash. And I'm holding, trying to keep my hand still. And verify. Verify, really important when you've got a connection like this. There we go. And there's our read. So that's not bad. However, holding that in place while doing a program, not fun. Ask me how I know. I did it while I was testing for this video. So I'll show you this crazy ass setup that you can also do. If I get out my bench vise and we just balance this bad boy on the edge of the motherboard. There we go. So I've used my bench vise here just to hold it in place for me. So this looks kind of sketchy, but once you've got things in position, it's kind of fine, to be honest, and it solves the hands-free problem. I am aware that some of the superstar technicians, they have elaborate vice setups to get pins onto the side of all kinds of chips for embedded controllers and PCHs and things like that to do firmware flashing. So this isn't that insane. So that's how that setup might work. Right, let's get this guy out the way now. Now, the other issue that you might run into when you're trying to do in-circuit flashing is if your programmer can actually power up the motherboard. Because the problem now is that not only are we trying to power up the chip that we want to read from, the chip isn't the only thing in that circuit, and there are other things on the circuit that are also going to suck up power from your programmer. Now, if you've got a beefy programmer, like an XG Pro, that's probably not going to be an issue, and in the worst case scenario, the XG Pro programmers have a DC in jack, so you can give them auxiliary power to help them power up grunty circuits. But if you're trying to do this with a tiny little CH341A, this guy ain't going to power up a motherboard. So the simple solution there, if you're programming a desktop board like this, is have the ATX connector plugged in and just turn on the power supply. So just click on the power supply so you have standby power, and the motherboard will power up the BIOS chip. And that way you can read from it and your programmer isn't having to power the chip. It's just reading and writing from it. And that will usually get you around that issue. However, the issue is that on laptop motherboards, there are various other things that you've got to watch out for, because the issue with in-circuit flashing is you don't know what else is there, and you don't know what else might be getting damaged or where the power from your programmer could be going. So there are little gotchas there. So let's do the final one. So the final test I'm going to do is using the SPI cable. So let's reposition for that. So for this one, I'll use a different programmer for a change. I'll show you the CH341A, just so you can see some alternative software, but also just so you can see a speed comparison between the slowest programmer I own and the fastest program I own, which gives you an idea of how much of a problem that may or may not be. Let's see, I'm going to make sure this is the right way around. Pin 1 needs to go that way around. Now for the CH341A, I use Neo Programmer. So once again, we're going to auto-detect the chip. And it has automatically detected a W25Q256JW. And just as a note, I've got the level switch on 1.8 volts already. Remember, if you have the black PCB version of this programmer, you will need to be using a 1.8 volt adapter for a chip like this one. So don't forget. It's worth noting that most chips will survive an overvoltage event. They're pretty rugged, these chips, but don't push your luck, because if you kill the chip, then you've got a bigger problem. And also remember, you don't know what else is on that rail. So if you just blindly pump 3.3 volts into the board because you're like, the chip will be fine, you don't know what else is there that isn't happy with 3.3 volts. So yeah, don't be a cowboy. Anyway, let's select that and let's go for a read. So we're now reading the memory. And right away, if you look at this progress bar at the bottom, you can see how much slower this programmer is. So yeah, I'm going to pause while I wait for this to read, because I'm not going to hang around. It is done. So what I'll do is I'll open up the backup that I made with the 2024 BIOS on it. So let's open this, and I'm going to write this one back to the chip again. So we're going to downgrade the motherboard back to the old BIOS. So this is purely just as a proof of concept thing, just to show you that using this method you can downgrade BIOSes as well, even if the BIOS system does not allow you to. It's worth keeping in mind that, remember, when you update a BIOS, you are also potentially updating other things on the board as well, like EC firmware and stuff like that. So this doesn't guarantee that downgraded BIOSes are going to work. But personally, I haven't actually seen an instance where it doesn't. So make of that what you will. Right, so we're now erasing the chip and we're going to write the data back to it. So I will see you in another 5 to 10 minutes. And we're done again. So let me just quickly rip all of this out and we'll turn it on one more time so we can get to the BIOS screen, and I can prove to you that this motherboard still works after I've messed with the BIOS 3 times in a row. Right, and as you can see, we're back in the BIOS and we're back on the 2024 version BIOS. So you can see that our flashing was successful again. So that's how we can reprogram the BIOS in 3 different ways without using the traditional built-in methods. So that's the end of this particular video. So for here, we've covered the basic hardware that we would use on it. So programmers, the kinds of adapters that are needed, and the general approach and the kind of software that we're going to be working with. In the next videos, we're going to be looking into what data is contained within that BIOS image and how we can start manipulating it. And in addition to that, we're also going to discuss what that BIOS image actually does when we switch on the computer, and how the PCH interfaces with it. So I hope you guys found that interesting. In the upcoming videos, we're going to be discussing not just how the BIOS starts and initializes the motherboard, but also what data is contained within that image and how we can start manipulating it. So big shout out to all my Patreons, Twitch subscribers, and YouTube channel members for supporting the channel. It is through all of that that I have time to do the more in-depth advanced projects like this. So I'm going to be looking to I'm going to try and get deep into this one. Thank you all for tuning in, and I'll see you next time. Bye for now.